Thank you very much. All right. As said, my name is Martin. I'm the co-founder and technical lead at Zircuit. It's a great pleasure to be here, great honor to speak right after Carl, because I'll be picking a little bit at his and Optimism Labs work. This talk is going to be about abusing. It's actually going to be about abusing the shit out of the OP stack to do something that it wasn't meant to really do, and it's to build a zero-knowledge rollup. So we did that. That rollup is called Zircuit. And we usually say that Zircuit is a novel EVM equivalent zero-knowledge rollup that focuses on security and brings more security, AI-powered security, to the sequencing protocol. So today, I want Zircuit to be something different. I want Zircuit to be a zero-knowledge rollup that is built on something unexpected, and that's the OP stack. OP here stands for optimistic, right? So we are actually marrying two technologies that are not really meant to work together, and this talk is about the challenges that this entails, just in case you wanted to do something similar so that you know what you are getting into. So a little bit of recap. We distinguish between two families of rollups, right? We have the optimistic rollups and we have the zero-knowledge rollups. In optimistic rollups, or in both the families of rollups, we have some actor called sequencer. The role of the sequencer is to collect transactions either from the users or from the L1. Then take those transactions, somehow order them into the sequence so that blocks can be formed. So the sequencer essentially forms your layer 2 blockchain. Then we have another actor, that's the state proposer. So state proposer, every once in a while, takes a look at the state root of the blockchain that is formed. That's your layer 2. It's going to take this state root, and it's somehow going to record it onto L1 inside of some kind of a smart contract, right? And then in the case of optimistic rollups, we have another role. That's the challenger in here. And the role of the challenger is to be watching those outputs that the state proposer records on L1. And if it notices that something was done wrong, the way how Carl was describing that he's producing those dishonest outputs, it is supposed to provide a proof that this was actually done wrong, and that would result in rolling back the state, right? And the challenger, it has some window of opportunity to do so. That's the 7 days. So anything that is younger than 7 days cannot be considered fully final. Everything that is older than 7 days means that it's final, because the challenger no longer has the opportunity to come and say, hey, this is wrong, we are going to roll it back, right? So you reach the finality after 7 days. On the other hand, with the zero-knowledge rollups, we are proceeding a little bit differently. Again, we have some role or actor called the sequencer. It collects the transactions. But before giving the state proposer the opportunity to grab the state and submit it onto L1, we did one intermediate step that's called proving. So before the state proposer comes, we grab the state, we give it to some actor called the prover, and the role of the prover is to produce succinct mathematical proof that the transition function of the blockchain was applied properly, that this state is in fact valid, and give that together with the state to the proposer who submits it onto L1. On L1, instead of just submitting it and letting the state sit and wait for a challenge, we have a smart contract, and the role of the smart contract is to verify that the proof is in fact valid, and only if it is valid to accept it and include it in the state. What you get for this extra work of proving is immediate finality, right? You have the mathematical proof that this state is actually correct. So this is the distinction and difference between a zero-knowledge rollup and an optimistic rollup. Now, imagine that you actually want to build a zero-knowledge rollup. There is a whole bunch of teams working on some kind of rollup out there right now. So you probably won't be starting from scratch, right? You will be looking at what other people did, how they did it, and you don't want to reinvent the wheel. So you will be starting from something. And what you will probably find is that you will need two basic things. You will need the node infrastructure, and then you will need some form of a ZK EVM or some form of the prover, right? So for the node infrastructure, you have this fantastic framework pioneered by the Optimistic Labs called the OP framework. And that framework is going to give you the sequencer. is going to give you the batcher, right? That's the guy that is taking a look at transactions, somehow compiling them together, and at some point submitting them to the data availability layer. That's called, or that's what the acronym DA stands for in here. Then you will get some smart contracts. Those are the contracts that you are submitting the stuff to that reside on L1. You will get the bridge, and you also need something that will be maintaining that layer 2 chain for you, right? So you will get some version of Geth or L2 Geth. And then if you want to actually get a zero-knowledge rollup, you will need that zero-knowledge machinery. So you will need to generate the zero-knowledge proofs. Again, as I said, there's a whole bunch of teams working on such stuff out there. And one thing that you might find are the circuits or ZK EVM provided or developed by the privacy scaling explorations based on Halo 2. So inside of there, you will find a whole bunch of opcodes split into some individual circuits that prove various statements about the transition function. And out of that, you can actually generate a smart contract that will be capable of verifying those proofs for you on-chain. Well, so it seems that this is simple, right? You just like plug these things together and it will work. Well, this talk is about the fact that this is not as simple as it sounds. So once you start diving deeper, you will realize that inside of the node infrastructure, the sequencer actually needs some special privileges for injecting transactions so that the entire optimistic protocol or the OP stack can work. Then you will find that the batcher and data availability doesn't really, tie directly into the stuff that the circuits and circuits provide you. Those are the zero-knowledge proofs. You will also realize that the smart contracts and the bridge are not as modular as you would like them to be, and once you start making changes, it's going to be a little bit difficult. And you will realize that the Geth itself for managing the state of that L2 was and needs to be changed, which is going to come eventually and bite you in the butt. On the side of the zero-knowledge proofs, as I said, you will get a whole bunch of implementations for the opcode that actually implement the ZK EVM. But you will not necessarily get the precompiles out of that. I will speak about that a little bit later. Then you will realize that those individual circuits are not necessarily connected together, so there might be some coherency missing. And when you want to generate your verifier, that's actually not such a simple task. It entails a few steps, and it might not be as quick as you think that it will be. And even when you have these two things somehow together, there is a whole bunch of other stuff that is still missing, right? So you will require some infrastructure. There will be some documentation hiccups in the process. You will need some front ends. And if you want to do good engineering work, you will also require tests. So in the rest of the talk, sad that it's a little bit broken on the slide, I will be talking about these topics a little bit in detail, and I will be going through them as those individual challenges. So let's talk about the first one. When the OP stack was being developed and architected, the authors very clearly needed to make some decisions, architectural decisions, right? So these somehow represent problems. The first problem is that the sequencer injects transactions into the chain. So the OP stack, it actually has two types of transactions that need to be injected. One is so-called system transactions. I'll be talking about those on a separate slide. The next one are so-called deposit transactions. The deposit transactions are the ones that we use to bring some assets from L1 onto L2. Well, none of these transactions are actually paid or paid in the EVM equivalent way. So for system transactions, again, to be covered them a little bit later, the system would need to pay gas, but you are the system, right? Your sequencer is the system. So somehow you're going to make up gas for yourself and pay it immediately back. But hang on, the EVM doesn't just let you make up gas or fund an account with artificial gas. That is an invalid operation, and that is something that the proofs that you're trying to generate should fail on, right? So this is not cool with us. Same thing, we have the deposit transactions. The deposit transactions, they're actually submitted on L1. They bridge those assets. That may be ETH, that may be NFTs, that may be ERC20 tokens. But the point is, they are submitted and paid for on L1. And on L2, that should just happen through the privilege of a sequencer to insert those transactions. Again, they are not paid on L2, so your circuits will need to complain about that, and you will need to change the circuits so that they are not EVM equivalent in this sense. And then you have a whole bunch of services that suddenly, before they were optimistic, right? So they didn't have to worry about any kind of proving, any kind of proofs flying around, any kind of data related to that. Well, now they do. So the batcher needs to know, the proposer needs to know that it's no longer proposing just a state and some transactions, but it also has some zero-knowledge proof with it. The data availability might need to be changed a little bit so that all the data that you need to reference inside of your proof during the verification is available and therefore can be somehow checked during the verification process. So in general, these services, they were not designed for zero-knowledge integration. There is various frequency in which they are supposed to act and do something, and the interfaces generally do not match. You will have to change that. The frequency will hinder you in terms of performance, and then the interfaces, they just need to be adapted. Then you will get the smart contracts. So I said the smart contracts are not as modular as you would like them to be. A great example of that is the bridge. So when I was talking about the zero-knowledge rollups versus optimistic rollups, we said that in the optimistic rollups, we have 7 days of waiting for finality. In zero-knowledge rollups, the finality is achieved immediately. So when you're withdrawing from an optimistic rollup through the canonical bridge, you need to initiate a withdrawal, then you have to wait 7 days, and then you have to complete the withdrawal. This is not necessary in the zero-knowledge rollups. The moment your state is rolled up together with the proof, that's the moment when you can start completing the withdrawal. So there is a whole step that is kind of skipped, and you will want to implement that in your smart contract. So you will want to remove that window of waiting for 7 days. Well, turns out that the OP stack actually comes with a whole bunch of quality of life tools. That's called the Optimism SDK. Those quality of life tools, they serve the purposes of checking the status of the blockchain. So, is this given block final and like hardcore final, or can it ever be rolled back? And as soon as you start modifying the smart contracts, you will realize that those are actually very closely coupled with the SDK. So you will have to start modifying the SDK as well. Then you will learn that Geth itself, that's the component that is managing the state of that L2 chain for you, was changed as well, right? It was changed because it needs to support some optimistic operations right now, such as inserting the transaction. But then once you start modifying it so that it can support your zero-knowledge rollup, you are starting to bring in new features that were not there yet. And where you end up is that you end up merging a few stacks together. Right? And this is definitely not trivial. And it's specifically not trivial once you realize that that Geth that is part of the OP stack is actually used both for communication with L1 and for communication or maintaining the state of L2 that you need to run some zero-knowledge proofs on. So the Optimism team, they're actually doing a great job keeping up with the development of Geth. Right? We had the Denkun update last week, and they already are supporting these transactions. This is fantastic. This is exactly what we want. But this is exactly what we want when it comes to the communication with L1. When it comes to the maintaining of the state of L2, you realize that you suddenly have that close coupling together with the circuits. And so you kind of sort of want your L2 Geth to be frozen in space and time, because if it is not, you will need to be upgrading your prover all the time whenever there is some update with Geth. Unfortunately, in the OP stack, there is only one Geth. It's used as a dependency on both. So for example, when you are rederiving that state, how Carl was saying, it's actually deserializing some transactions from L1 into the same data structure that are used to actually produce traces for the zero-knowledge machinery and so on. So this is a little bit of a problem. Then I was talking about the deposit transactions. So those are the transactions that we use to bridge assets, such as ETH, right? So I already said that those transactions are paid on L1, not on L2. The way how it works is that you show up to L1, you say, hey, I want to bridge some amount of ETH, so you send that ETH to the bridge, and then on top of that, the system is going to burn some extra gas for you, and that's going to signify that you have paid the dues that you would normally pay on L2, because you cannot pay anything on L2. You don't have any ETH there yet, right? So that wouldn't make sense. So those are the problems with payments, and I already touched on that a little bit, but those are not the only problems that relate to the deposit transactions. So the problem with these deposit transactions are that in the OP stack, they're actually not included in the state of any smart contract, and they are not included in the state of the blockchain in the sense that would be accessible to smart contracts, specifically the verifiers, when they need that, right? What happens is actually when you bridge, the stack is going to emit some events. Those events are going to be read and detected on L2, and then the sequencer is going to inject those artificial transactions. Well, guess what we need to do in the zero-knowledge setting? We have to make sure that the sequencer didn't make it up, right? That it didn't inject some transactions because it has the privileges to inject them. So once your proof comes, you would somehow like to reference those transactions from the verifier contract, but as I just said, that is not possible because all that you have available are those events or some call data that is available in some kind of an address. So you have to engineer for that, and you have to somehow reflect it in your zero-knowledge circuits. And again, Geth itself, it does require changes. It does require the ability for the sequencer to insert some transactions. That is not, in general, EVM equivalent. So it is going to further complicate your circuits. Suddenly you will realize that those beautiful EVM fully equivalent circuits provided to you by the PSC repo no longer work. You will need to change them and divert away from EVM. Not something that you would normally expect. Cool. So back to the smart contracts. So at some point, throughout your life cycle, you will realize that you want to change them because, you have started with some design, but it's no longer good enough. Maybe if you swap the proving system a little bit, you would be able to generate your zero-knowledge proofs in a faster way. And you might start making more and more modifications. Well, everywhere you touch those smart contracts, you will realize that there is some very close coupling and that there is no single interface that would constitute a zero-knowledge rollup or an optimistic rollup that you would just need to implement and everything would suddenly work, right? So you will find yourself in the struggle of modifying those smart contracts all the time and modifying everything that ties to them, which I already mentioned is, for example, the SDK, plus the other services that are part of the rollup itself. Then, if you start with the OP stack as you currently find it in the repo, you will find that it contains some legacy code. The situation here, has definitely improved. The repo has been cleaned up quite a bit. But the point here is, one thing that we all love about the OP stack is that it is battle tested, right? There is mainnet out there. It has been running for some time. We know that this thing actually works. Well, because there is a mainnet out there, and because Optimism also evolved, they went through some migrations of the state, some upgrades, some improvements, and so on. So you will find a lot of code that actually relates to backwards compatibility, which is important for Optimism and rollups that are upgrading, but it's not necessary for the rollups that are just starting, right? You will probably not going through 2 or 3 upgrades just so that you can start your rollup fresh from zero. You will want to start with the most up-to-date code. Finally, as I said, bridging is not zero-knowledge feature complete. That's not surprising at all. Again, we are abusing the optimistic stack in here and trying to do some zero-knowledge stuff, right? So what you would specifically want to have more with respect to bridging is the ability to make some statements and claims about the amount of ETH that was bridged, right? You will have to somehow prove that the sequencer didn't make up how much ETH should be issued to this given account on L2. Cool. So system transactions, that's the second type of transaction that is inherently necessary inside of the OP stack. What do? Here up there, you can see what they do. They actually take some values from L1, such as the block number, such as the timestamp, such as the base fee, and so on, and then they record them into a smart contract on L2. This is a design choice that was done by the Optimism team. You could philosophically debate whether this is the best design choice, but definitely this happens. It definitely also happens in every single block of L2. So every single block of L2 will take a look at L1. The block time, the default block time of the OP stack is currently 2 seconds. All the rollups out there do some sort of a similar time, be it 3 seconds, be it 5 seconds, be it 4 seconds, doesn't matter. It certainly moves much faster than these values change because L1 moves slower, right? So you are several times repeatedly recording the same values over and over into a smart contract. On top of that, you're not paying for it, right? I already mentioned that several times. But on top of that, these are transactions. So you actually need to generate some of those zero-knowledge proofs for that. You need to post this data onto your data availability layer, and you need to verify the proofs. So that all increases the operation costs, and eventually it will increase the cost for transaction for the user, right? So you sort of need to engineer against that and consider some alternate designs. Otherwise, this is going to be a general problem. So here, I'm on slide 15, and so far I haven't told you anything about the challenges that relate to the zero-knowledge proofs. We were just through the node infrastructure, right? So yes, you will get your ZK EVM through some repository that you might find online, be it maybe the one from the PSC, be it a different one. But what you will learn once you start implementing and marrying things together is that you didn't get everything that you need. You have some opcodes that are implemented, right? You will get a whole bunch of circuits, something like 8 of them, that are ready to prove some individual claims, but that's about it. So the opcodes themselves, they will be implementing the EVM, but EVM is not everything that is currently available on Ethereum. Specifically, what you will not get are the precompiles. So precompiles are some smart contracts that are included on predefined addresses. Ethereum currently has 9 of them, so addresses 1 up until 9. And those are, let's say, some more complicated cryptographic functions that would normally cost a lot of computing power to produce, and they would be expensive for gas. So therefore, what we are doing on Ethereum is introducing smart contracts that they actually implement these features, and we price them a little bit differently. So you will not get the precompiles because not all of these precompiles are zero-knowledge friendly, and you would have hard time generating zero-knowledge proofs for that. So you will have to address it somehow. And if you want more functionality or more precompiles, that somehow has to be addressed as well, and you will have to develop more and more. You might find yourself diverting from the EVM equivalency more than you would originally envision. Then I said that you will get those individual circuits, right? So let's say that you have 8 circuits that are capable of very quickly proving some small claims about your transition function and the transition of the state. Well, you don't want to be posting all those individual proofs on chain 8 times, right? Every single posting, every single transaction, every single verification is going to cost you gas. So before you do that, you will want to aggregate them somehow, right? So take those 8 proofs and produce a different proof that proves all of them at the same time. Well, that is easier said than done, because while, yes, you can do this, there are actually aggregation systems out there. You just by the fact that you've merged 8 proofs together will not really get a proof of one claim that you wanted to prove. Specifically, what will be, for example, missing is the data coherency. You will not, for free, get the fact that all of these 8 proofs that you've just merged together were produced using exactly the same inputs, right? Again, you will have to somehow engineer for that, and you will have to reflect it in your code. In general, You might also have to make some changes to your geth because not everything in Ethereum, specifically the hashing function, Ketchak, is zero knowledge friendly. There are other functions and other things that might be a little bit more efficient for you in terms of performance. So finally, once you've covered all your angles, you have the node infrastructure and you have your zero knowledge EVM, this still doesn't mean that you have a full rollup, right? You need to run this somewhere and you have to make sure that everything is operated in some reliable manner. So you will need to orchestrate the blockchain and the prover generation and the state proposer into some pipeline. So you will need some infrastructure. Then depending on how exactly you have designed your zero-knowledge EVM, you may need some specific hardware that allows you to produce these proofs in an effective manner. Or the other way around, if you have already purchased some hardware and you are bound to operating on certain infrastructure, you might actually completely need to redesign your zero-knowledge EVM so that you can operate on the given hardware. Now, if you want to do good engineering work, it doesn't end with code itself, right? There is a whole bunch of other stuff and artifacts that you might need to produce. So I'm calling it nice to have, but it's actually not nice to have. These things are necessary for well-developed systems. So you will need to test your code, but you will not only need to test your code, you will also need to test your zero-knowledge circuits. Now imagine that you're trying to produce unit tests or integration tests for something where a single run lasts for 20 minutes or 30 minutes, and that's just a single run. And it might require expensive hardware and GPU and something else, right? This is not an easy thing to overcome because you will suddenly need to employ a lot of mocking and various advanced testing techniques. But if you're mocking out the generation of your proofs, well, what are you really testing in here, So this is definitely a challenging problem. You will be struggling a little bit with the documentation because as I said, the system had some evolution in the past, right? So you will be finding documentation that is obsolete. You will be finding features that are not really documented anywhere, and you will somehow have to deal with it and fix it for your system. And in the end, you will also need some Web2 components, right? Because people will not be interacting directly with your sequencer or directly with the smart contracts. They will want interfaces, they will want block explorers, and so on. And finally, even once you have that, well, you will need to operate it, right? Software itself doesn't constitute an operating system, so you will need to deploy it somewhere. You will be running a whole bunch of services, and you will need to keep consistently make sure that all of these services are up and that your chain is not down because one of these services is not progressing or is slow. So I'm getting a signal that I'm out of time, so I will skip this slide. In general, if you want to have a rollup that has some future, you will need to also think about the future. So you will need to make some cryptographic improvements that relate to the generating of zero-knowledge proofs and performance. You might also think about some new features that your rollup wants to have. But that's it for my talk. So just to quickly summarize, OP-Stack, it's a fantastic starting point. It's one of the best frameworks that exists out there that is generally available. If you want to build a rollup, I can heavily recommend it, but be aware that it's a starting point. You will need to make some changes. You will need to do a lot of research, especially if you want to produce a zero-knowledge rollup, but nothing in here that I have mentioned is not something that you couldn't overcome. And then part of what I wanted to talk about is some security stuff, but I will not have time for that at all. So thank you for the attention. If there are any questions, if we have time for questions, I will be happy to take them. Otherwise, thank you.